And now we come to the heart of structures class, equilibrium. You'll recall that at the start of the term we talked about Newton's 3 laws of motion, and the third one was equilibrium, which says, for every action there is an equal and opposite reaction. This book is Structures, or Why Things Don't Fall Down. It was written by a cranky old British engineer back in the 80s, and it's been kept in print because people like it. Let me just read this to you. If a material or a structure is to resist a load, it can only do so by pushing back at it with an equal and opposite force. If your feet push down on the floor must push up on your feet. If a cathedral pushes down on its foundations, the foundations must push up on the cathedral. This is implicit in Newton's third law of motion, which, it will be remembered, is about action and reaction being equal and opposite. In other words, a force cannot just get lost. Always and whatever happens, every force must be balanced and reacted by another equal and opposite force at every point throughout a structure. This is true for any kind of structure, however small and simple, or however large and complicated it may be. It is true not only for floors and cathedrals, but also for bridges and airplanes and balloons and furniture and lions and tigers and cabbages and earthworms. If this condition is not fulfilled, that is to say, if all the forces are not in equilibrium or balance with each other, then either the structure will break, or else the whole affair will just take off like a rocket and end up somewhere in outer space. So this class is really about statics, which is the action of forces on rigid bodies that are not moving. And why are they not moving? Because they are in equilibrium. And that's how you can tell something is in equilibrium. It's not moving. So all the forces and all the moments in every direction are in equilibrium if the thing is not moving. Here at the top are two people on a teeter-totter, where the moment of one person balances the moment of the other person. They're in equilibrium and they're not moving. The one at the bottom is not in equilibrium, so it's out of balance and stuff starts to happen. Equilibrium, not equilibrium. And equilibrium comes from two Latin words meaning equal and balance. So this thing is a Libra, it's a balance scale. Equilibrium means it's in equal balance. And you can see this demonstrated in something like a tower crane, where they're lifting a heavy weight out at one end, and so for equal and opposite reaction, they put big chunks of concrete on the other end for balance. So now the equilibrium equations, which are super simple. If a thing is in equilibrium, it's not moving, and all of the forces in any direction, no matter what direction, all add up to 0. And you could write that this way. The sum of all forces equals 0. And not only all the forces, but all the moments on a thing that's not moving have to add up to 0. And you could write that this way. The sum of all moments equals 0. And that's true for anything that is not moving. Usually, it's handy for us to break forces into x directions and y directions, x components and y components, because they're square and they're easy to handle. So when we say equilibrium equations, usually we mean this. Sum of all forces in the x direction equals 0, sum of all forces in the y direction equals 0, and sum of all moments equals 0. These are the tools in your toolbox. Thinking back on our kids with the 2 ropes pulling on the front of this wagon, if a third kid came along and hooked up another rope on the back of the wagon and pulled straight backwards, let's say with 14 pounds, what would happen? What would be the net result? All those forces in the x direction would add up to 0. These two kids pulling forward on one side, that kid pulling backward on the other side, all the forces add up to 0, and as a result, that wagon is not moving. Here are some people having a tug of war on the grass, and at the moment I came along with my camera, their forces were in balance and nobody was moving. They were just kind of frozen in space there. In other words, the sum of all their forces in the x direction added up to 0. So you could make a diagram of that, which our book has done here. The sum of all the forces in all directions, in this case the x direction, all those forces are adding up to 0. Here's a picture of my friend the spider hanging from a spider web. I like these guys. And here's a picture of the forces in that spider web. Here's the weight of the spider hanging down, and here's the equal and opposite reaction of her web pulling back up. And whatever thing you're pulling on, there's an equal and opposite reaction going the other direction. And if you wanted to insert one of these spring scales in the middle of a rope, we used to use these in the filbert orchard where I grew up. We'd hang sacks of filberts from them, but you can hang anything from them. And so you could cut a rope somewhere, stick that spring scale in there and measure the force, and it would measure, in this case, 30 newtons. You could cut that rope someplace else and put that scale in there, and it would still be 30 newtons. Any place along that rope, it's going to be the same. So this is Newton's third law of motion, equilibrium. For every action, there is an equal and opposite reaction. When a building presses down on the soil pushes back with an equal and opposite reaction, and that's why the building does not sink into the soil. If you are, let's say you weigh 140 pounds and you're standing on the floor is pushing back with exactly 140 pounds of reaction, and that's why you don't fall through the floor. And next term we'll look at how the floor does that. So all of the forces add up to 0, and it doesn't matter which one you call the force and which one you call the reaction. A lot of times when we have a beam with a force on it, with a load on it, we'll say, okay, this load is the force, and the holding up forces, we'll call those the reactions. But we could call them other things. Oops, sorry. So this is Newton's third law of motion. For every action, there is an equal and opposite reaction. For example, this is a picture out of our book. If a building has a weight sitting on the soil pushes up with an equal reaction. If the soil doesn't have enough bearing capacity and to push back up with that much, the building will sink into the soil. And if by some miracle the soil were pushing up with more reaction than the building were pushing down, then the building would go off flying. You would have levitation. You could measure equal and opposite reaction with a couple of kitchen scales if you want. So here is a soup can sitting on top of a book spanning 2 kitchen scales. And if you put the can of soup in the middle, each scale will register half the weight of the can in the book, so those two are equal. If you move the soup can off center, the loads are not equal now. There's less weight on one scale and more weight on the other scale, but the two of them together will still add up to 1 can of soup plus a book. Here are 2 people on a teeter-totter. And if they're just balanced there, the sum of all moments add up to 0. And what are they? Well, we've got this person on the left, 80 pounds times a distance of 6 feet. Then we've got this person on the right, 80 pounds times a distance of 6 feet. And notice I put a negative sign in there. Those add up to 0. Recall that if a moment is rotating counterclockwise, we call that positive moment. If a moment is rotating clockwise, we call that negative moment, hence the negative sign in there. So you could go 80 times 6 is 480 foot-pounds, minus 80 times 6 is minus 480 foot-pounds. 480 minus 480 adds up to 0. Ha-ha, that teeter-totter is in equilibrium. Now, how big is the reaction? How big is the holding up force? Well, here's another tool in our toolbox. The sum of all forces in the y direction equals 0. And what have we got? We've got 80 pounds pushing down, so I made a negative, and 80 pounds pushing down on this side, so I will make another negative, and a reaction pushing up in the middle, and all of those add up to 0 because the thing is not moving. So we could go minus 80, that's minus 160, plus the reaction, that adds up to 0. Now, if we add 160 to both sides, they're still equal. Those 160s cancel out, and we are left with the reaction equals 160 pounds, which makes sense because there's two 80-pound people. So there's the reaction. Now, how about the moments? These two people have different weights and they're sitting at different distances, but it looks like that teeter-totter is in equilibrium. It's not moving. So the sum of all moments equals 0. We've got 80 pounds times 6. We've got minus 160 pounds times 3. And those add up to 0. And I did those signs because counterclockwise is positive, clockwise is negative, and those add up to 0. So 80 times 6 is 480, minus 160 times 3 is 480, so 480 foot-pounds minus 480 foot-pounds adds up to 0. Ha! This is in equilibrium. Now, how big is the reaction under here? You might begin to see the pattern here. It's just whatever those two add up to. So the sum of all forces in the y direction add up to 0. And what are they? We've got 80 pounds going down, and a reaction pushing up, and 160 pounds going down, and those all add up to 0. So minus 80 minus 160 is minus 240, plus the reaction. Those add up to 0. If we add 240 to both sides are still equal. Those 240s cancel out, and we are left with the reaction equals 240 pounds. So there's our diagram. There's our reaction, 240 pounds pushing back up. That's the equal and opposite reaction.